Hi, today we are going to discuss particle in a one-dimensional potential box. Consider a particle of rest mass m enclosed in a one-dimensional box. The particle is present along the x-axis where the potential box first boundary is exist at x is equal to 0 and second boundary exists at x is equal to L. At the boundaries, the potential energy is infinity. At that moment, psi value is 0. Similarly, outside the potential box, the potential energy is infinity and psi value is 0. But inside the potential well, V is equal to 0. Therefore, psi naught is equal to 0. These are the conditions. At that situation, if a particle is existing inside the potential box, then we have to calculate its energy and wave function. That is the aim of this concept. So first we are considering the boundary conditions. In these boundary conditions, we will represent where V is equal to 0 and where V is equal to infinity. So according to our diagram, inside the potential box, the V value is 0, means 0 less than x less than L. In this region, the potential energy is 0. And the potential energy is maximum at the boundaries or outside the boundary, means the potential energy infinity at the boundaries or outside the boundary, that is 0 greater than equal to x greater than equal to L. Similarly, inside the potential box, the psi value is not is equal to 0. At the boundaries or outside the boundaries, the psi value is 0. So these are the boundary conditions. Next, we will go for showing the time independent wave equation. So in that equation, we are assuming that V is equal to 0 because the particle is available inside the potential box. So already we assumed that inside the potential box V is equal to 0. Therefore, the Schrodinger wave equation can be written as dou square psi by dou x square plus 2m naught by h cross square E psi is equal to 0. This is equation number 1. So here we are assuming that 2m by this is equal to k square. So then the equation can be written as dou square psi by dou x square plus k square psi is equal to 0. This is equation number 3. The solution for equation number 3 can be written as psi of x is equal to a sin kx plus b cos kx. This is equation number 4. Now we are going to solve this equation number 4 using first boundary condition and second boundary condition. Now we are implementing the first boundary condition. That is psi is equal to 0 and x is equal to 0. So this is nothing but this is the first boundary where the potential will exist. That is x is equal to 0 and psi is equal to 0. So these values we are substituting in the psi of x is equal to a sin kx plus b cos kx. Means in the fourth equation we are substituting. If we substitute these values, then we will identify that the b value is equal to 0. Now we are substituting b value in the fourth equation. Then we will get a fifth equation, that is psi of x is equal to a sin kx. This is the fifth equation. After this, now we are applying the secondary boundary second boundary condition. So in the second boundary condition, it indicates that where the second boundary is existing, we know that the width of the potential well is small, capital L, and the second boundary is existing at x is equal to L, and at that moment psi value also 0. Now we are substituting these values in equation number 5. Then we will get 0 is equal to A sin KL. So in the equation A is a constant, so A naught is equal to 0. Therefore, sin KL must be equal to 0. Then that equation can be written as sin KL is equal to sin n pi, because sin n pi is nothing but 0. Instead of 0, we are writing sin n pi, because sin pi value, sin 2 pi, sin 3 pi dash dash up to sin n pi values are 0. Therefore, sin n pi is nothing but 0. So instead of 0, we are writing sin n pi. So therefore, what happens? Sin can cancel. So in the next step, we will get KL is equal to n pi, or K is equal to n pi by L. So we will get the equation number 6. After this equation, we are writing this K value in the wave function value. So psi of x is equal to A sin n pi x by L, where n naught is equal to 0, but n is equal to 1, 2, 3 dash dash. Now we have a equation, second equation, that is already we know that this is the second equation, that is K square is equal to 2m naught E by h cross square. But already we know the K value, that is the n pi by L. So this value we are substituting here. So n pi by L whole square is equal to 2m naught E by h cross square. So this, from this we will identify we will calculate the E value. That calculated E value is equal to n square h square by 8m naught L square, where n is equal to 1, 2, 3, 4 dash dash. So this is the final equation. In this case, n is equal to 1, 2, 3, 4 dash dash. So if we substitute n is equal to 1, then E1 can be written as h square by 8m L square. So that energy is called as 0-point energy, or we can say that it is a ground state energy. Now we have the psi value. Psi of x is equal to A sin n pi x by L. Now we have to identify the capital A value. For that purpose, we are using normalized wave equation, that is equal to integral minus infinity to plus infinity mod psi of x whole square dx is equal to 1. So we have to submit these values in this equation. Then a square integral 0 to L sin square n pi x by L dx is equal to 1. The simplification of this equation is nothing but A is equal to under root 2 by L. So now we are substituting this A value in the above equation. So this is the A value. So we are substituting this A value here. Then it can be written as psi nth of x is equal to under root 2 by L sin n pi x by L. So this is the final equation for this one. So in that way, we calculated energy of the particle and wave function of the particle. Based on these values, if we draw a graph energy versus energy levels, then we will get the first diagram, that is A diagram. In the A diagram, it is observed that x-axis is nothing but, this is x-axis where the potential energy, the potential box is parallel to the x-axis, And here we have energy levels are there, different energy levels are there. And our formula is equal to E is equal to n square h square by 8m L square. Suppose if we substitute n is equal to 1, so that will be called as E1. And if we substitute n is equal to 2, then the value will be 4h square by 8m L square. So this is the equation. So this will be the E1 and this will be the E2. Similarly, if we substitute n is equal to 3, then it is E3. Similarly, now we are drawing a graph psi square versus x. Another one is psi versus x. So diagram B showing psi versus x. So x-axis, in this case, x-axis is x and y-axis is psi. So here we are getting some graph. So first one is represent the psi 1, second one is psi 2 and psi 3. So when we are substituting x is equal to 0, so we will get the 0. When similarly if we substitute x is equal to L, then we will get the psi value is 0. And at x is equal to a by 2, we will get the psi value is maximum. So therefore we are getting this type of curve. Similarly here also we are getting for psi square versus probabilities. Similarly, if we substitute n is equal to 2 for a wave function, then psi 2 is equal to under root 2 by L sine of n pi x by L. So from where these curves will represent where the probability of finding a particle is maximum, where it is minimum. So from this observation, it is observed that at x is equal to 0, at x is equal to L by 2, at x is equal to L positions, the probability of finding a particle is minimum and the remaining parts it is maximum. And here we observe that at x is equal to L by 4, the probability of finding a particle is maximum. Similarly, if for psi 3, it is observed that the probability of finding a particle is minimum at x is equal to 0, at x is equal to a by 3, at x is equal to L. And the remaining parts, the probability is maximum. So we observed that the probability is maximum at a L by 6 position. So in that way, we are representing psi square versus probabilities, psi square versus x, and psi versus x. Thank you.